Hello everyone, Mr. Hauk here. In today's video, we're going to be exploring radian measures. By the end of this video, we should be able to explain what a radian is, compute the length of a circular arc, and convert angle measures from degrees to radians and vice versa. Let's go ahead and get started. Let's consider the image to the right, where we have a circle with center C, and CA is going to be the radius of the circle. So we want to construct a point B on the circle such that the length of the arc, AB, is equal to the length of the radius, CA. Then, if we look at the angle formed, angle ACB, and we'll go ahead and just call this theta. If we look at the angle theta, the measure of that angle would be called 1 radian. So in summary, if a central angle, in this case theta, in a circle intercepts an arc equal to the length of the radius of that circle, the measure of that angle is 1 radian. So, how many radians do you think it would take to wrap all the way around the circle and get back to point A? Well, linked here in the notes is a little animation that explains just that, but let's continue to explore this concept of radian. So in this example, the length of each minor arc AB, BD, DP, PH, HK, and KM in the circle to the right is the length of the radius. We want to determine if the statements below are true or false. So again, just to clarify here, arc length AB, BD, DP, PH, HK, and KM are all the length of the radius of the circle. And by definition of radian, that means that angle ACB, angle BCD, angle DCP, angle PCH, angle HCK, and angle KCM are all measured 1 radian. So let's see which of these statements are true or false. Statement 1 says angle PCB has a measure of 2 radians. So if we look at angle PCB, well, since angle BCD and angle DCP both measure 1 radian, angle PCB combined will measure 2 radians. So this first statement is true. The second statement says angle BCH has a measure of pi radians. Well, we know that pi is approximately 3.14. And if we look at angle BCH, well, angle BCH actually is exactly 3 radians. Again, since angle BCD is 1 radian, angle DCP is 1 radian, and angle PCH is 1 radian. So this would be a false statement. And again, it's false because angle BCH is actually equal to 3 radians. Looking at our last statement, an angle formed by a complete rotation of a ray about its endpoint will measure 2 pi radians. So let's think about if we took point B and rotated it all the way around, what would the central angle measure? Well, it turns out that the central angle would actually measure 2 pi radians. And let's figure out why. So this would be true, but let's explore why that is true. So here in this example, we have a circle with center D, and we have a point F such that DF is the radius of the circle. Let's go ahead and call the radius R. So R is the length of the radius. And let's go ahead and construct a point G anywhere on the circle, so I'm just going to put it right here. And let's say that the arc, FG, we'll call that arc length S. So S is the arc length FG. And if we were to look at the angle that's formed between angle FDG, let's go ahead and call this theta, we want to come up with a relationship between the angle FDG, theta, the radius R, and the arc length S. So it turns out that theta, the measure of the angle, will be equal to the arc length S divided by the radius R. And one thing that we can do here is we can actually rewrite this equation to solve for the arc length S. So here, this is our equation for radians, the angle measure, and this automatically implies, if we multiply both sides by R, that the arc length S is equal to the radius times the angle measure. So that is another useful formula here. So this is our formula for arc length S, and this is our formula for the angle measure. Angle measure in radians. So now let's consider a central angle in a circle formed when the radius makes a complete rotation about the center of the circle. So let's say that we go all the way around the circle. What is the arc the central angle intercepts? Well, if we're going to rotate all the way about the center of the circle, then the arc that the central angle intercepts is the circle itself, which is very interesting. It's the circle itself, or the circumference. I spelled circle wrong. The circle itself, or the circumference. Well, how long would that arc be? Well, we know from geometry that the circumference is 2 pi r. So S, the arc length, would be 2 pi r. So using our formula from above, what would be the exact radian measure of the central angle? Well, let's go ahead and say, using our formula here, theta, because we're looking for the radian measure of the central angle, so that would be theta, is equal to the arc length S divided by the radius r. But we just identified the arc length S as 2 pi r. So we'll substitute 2 pi r for S. Notice that here, r will cancel in the formula, and we're going to get that theta is equal to 2 pi. So this is proof that if we were to rotate this point F here all the way around the center of the circle, that the central angle would measure 2 pi radians. So theta would equal 2 pi radians. Well, this lets us draw some interesting conclusions. So we just saw that the angle measure formed by a complete rotation is 2 pi radians. And we already know from geometry that the angle measure formed by a complete rotation is also 360 degrees. So that means that 2 pi radians is equal to 360 degrees. Well, notice that by dividing by 2 on both sides of the equation, this also implies that pi radians is equal to 180 degrees. So let's go ahead and use this relationship to derive a couple of very helpful formulas. So maybe I want to derive the formula for, what is exactly 1 radian? Well, if I wanted to isolate for 1 radian here, let's divide both sides of this equation by pi. And notice that if we divide both sides of the equation by pi, we're left with 1 radian is equal to 180 degrees divided by pi. So this is our formula for 1 radian. Similarly, let's say that maybe I wanted to find out, well, what would 1 degree equal in terms of radians? Well, if I divided both sides of the equation by 180, notice that we would get that 1 degree is equal to pi over 180 radians. So let's use these results to do a little bit of practice. So again, let's rewrite those just to have them for reference. We know that 1 degree is equal to pi divided by 180 radians. And we also know that 1 radian is equal to 180 degrees divided by pi. So we want to use these formulas to either convert degrees to radians or convert radians to degrees. So in our first example, we're going to convert 200 degrees to radians. So we have 200 degrees, but we know that 1 degree is pi divided by 180 radians. All right, well that's going to give us 200 pi divided by 180 radians. And simplifying 200 over 180, this would give us 10 pi over 9 radians. So 200 degrees is the same as 10 pi over 9 radians. Now let's convert negative 40 degrees to radians. So we have negative 100, we start with negative 40 degrees. Again, we know that 1 degree is equal to pi over 180 radians. So negative 40 times pi over 180 radians. This would give us negative 40 pi over 180 radians. And continuing to simplify, this would simplify to negative 2 pi over 9 radians. So we can see that negative 40 degrees would be the same as negative 2 pi over 9 radians. Now let's convert radians to degrees. So we have 7 pi over 8 radians. However, we know that 1 radian is 180 degrees over pi. So this would be 7 pi over 8 times 180 degrees over pi. Well, we can go ahead and simplify this a little bit. We can see that pi in the numerator and pi in the denominator will cancel since we're multiplying. And we can go ahead and reduce this fraction. 7 times 180 divided by 8 would give us 157.5 degrees. In our last example, we want to convert 2 radians to degrees. Again, we know that 1 radian is 180 degrees divided by pi, so we'll say 2 times 180 degrees divided by pi. And in this example, well, there's not much to simplify. 2 times 180 will be 360 degrees divided by pi, which is, we could have that as our final answer, but this is also approximately 114.59 degrees.